Hello everyone, my name is Kent and welcome back to my workshop. This is the second video in a two-part series to build a linear stage for positioning a camera under computer control. In the first video we examined the design and machined the custom parts. In the second video we'll assemble and test the linear stage. In a related video are details for machining a custom socket for tightening the ball screw retaining nut. I hope you enjoy these videos. Now let's assemble and test a linear stage. Starting an assembly by first laying out all the parts in an orderly fashion will make the entire process run smoother. Off to my left hand side is a full set of assembly drawings and bill of materials. All the parts have been checked against that bill of materials to be sure that we have exactly what's needed for this assembly. The hardware is also nicely organized and labeled. A miniature linear rail is being used. While the linear rail's capacity exceeds what's needed for this project, the linear rail still needs to be lifted so that the top of the ball nut block is parallel to the top of the linear rail carriage. To help with this, we use a height adjustment block which has an amazing number of tabbed and counterbore through holes. I could have machined this, but like much of the hardware, it also came from Misumi. I was attempting to minimize the amount of custom parts that needed to be machined. The carriage of the linear rail is secured in place with a couple of rubber bands. A large number of socket head cap screws secures the linear rail to the top of the height adjustment block. I think these socket head cap screws are low profile versions. There are little plastic fillers for these holes to try to minimize gunk accumulation on the linear rail. The video doesn't show the insertion of the caps, but you can see them at the beginning when we were looking at all the parts. The ball screw is supported by two blocks. This is a non-fixed block. On this side, the retaining ring secures the bearing block and ball screw assembly. Because only a retaining ring is used, the non-fixed side has a little bit of axial play while the fixed side does not. The black collar on the ball screw provides a contact point for the bearing inside of the fixed support block. A collar goes on each side of the block. The material of the base plate that all these parts are being attached to is acetal. I was not able to machine this part on my mill due to its size, and it was done by a plastics company. Because of the natural lubricative properties of the plastic, this is a bit of an experiment to see how well the screws will remain secure. This is the second of the two collars. A retaining nut screws onto the ball screw to provide preload on the bearings. A small brass insert under a set screw is used to secure the retaining nut to the ball screw. Sticking the insert to the set screw with a small amount of grease from the linear rail works well. Once the insert is in position, we can turn the retaining nut onto the ball screw. The retaining nut has a boss on one side, and that boss must press up against the collars. Misumi publishes torque specifications for the retaining nut on the ball screw so that the bearings are properly preloaded. However, they don't supply a socket to be used on the retaining nut. I'm not sure how this is supposed to be torqued. In a separate video, I designed and machined a socket adapter for this purpose. The Misumi ball screws can be configured to flats to aid with tightening the retaining nuts. In this case, a 9mm wrench on the flats will hold the ball screw. We'll torque the 10mm ball screw to 9.3 Newton meters. Tightening the set screw of the retaining nut ensures that it won't spin off. It should be possible to move the ball nut along the ball screw without much force. The ball nut must not be allowed to move onto the flats of the ball screw. Because of this, you may choose not to have the flats machined onto the ball screw. The default is not to have flats on the ball screw. If the ball screw does have flats, there should be some mechanical stop preventing the ball nut from ever reaching them. In this case, we'll use urethane bumpers. Beyond limiting the range of the ball nut and protecting it from the flats, the urethane bumpers are not necessary in this design. The linear stage will not move at high speeds nor with high power. The motor that we use may allow hard stop homing, and if that homing method is used, one would have to check if urethane bumpers are compatible with hard stop homing. Most, if not all, of the ball nuts that are available from Misumi are the cylindrical type with a flange. A ball nut block provides a flat surface to attach to the ball nut. A retaining ring is used to secure the non-fixed support block. This only loosely holds together the ball screw, the support block, and the bearing. The other support block, or the fixed side support block, is responsible for preventing axial backlash. The Misumi ball screws can also be configured to have multiple flats at the power end of the ball screw. This is especially nice with couplers like these that have two set screws 90 degrees to each other on both sides. The motor that we're using is from Schneider Electric. It comes nicely packaged with a screwdriver, but I don't think that screwdriver is suitable for any of the connectors that are on this motor. In another video, the NEMA 17 motor mounts are designed and machined. This motor is very convenient. It has a built-in encoder, driver, and controller. The motor also has multiple digital inputs and outputs, and one analog input. There's a number of different ways to send commands to the controller. I'm going to use text strings sent over Ethernet. The motor will be controlled by a Python program running on a computer. The Python program monitors the state of the motor and coordinates sending commands to it. This allows motor control to be abstracted away from a higher level program. Having digital inputs on the motor allows the proximity switch to be directly connected to the motor, further abstracting motion control. This design has iterated a few times and apparently overlooked the interference between the motor and the base plate. This problem immediately shows up in an interference check in SolidWorks. I simply had forgotten to run the interference check earlier. Thread locker is used to secure the dowel pin. Retaining compound would be stronger, but for this application, thread locker is fine. There's a little clearance and the dowel pin needs to be held in place while the thread locker sets. The relative placement between the dowel pin and the 1/4 inch through hole needs to be accurate with respect to the camera body. Unfortunately, Canon does not provide solid models of their cameras to build designs around. Instead, careful measurements of the camera body are necessary. Here are two of the parts that we made in the last video in this series. The camera plate is being secured to the bridge plate. And now we in turn mount the bridge plate, securing the ball nut block to the linear rail carriage. The ball screw support blocks are still loose and allowed to move, preventing binding. We'll secure them shortly, but it should now be easy to move the entire assembly. We can now mount the cable carrier. The cable carrier comes in at least a couple of forms, one where the wire is inserted on the outer part of the curve and another where the wire is inserted on the inner part of the curve. Cable carriers from Misumi can be configured to length up to a maximum. Beyond that length, multiples must be ordered, potentially in different lengths. Segments are easy to remove or add, and the ends can be rotated with a little modification. An inductive proximity switch will be used to create a reference or home position. Care must be taken when selecting a proximity switch. In particular, pay close attention to the sensing range. When examining the sensing range, be sure that the material that you're using matches the material that's in the chart. The sensing range that I had for this proximity switch was for steel, but the ball nut block is made of aluminum. For reliable sensing, I later needed to raise the proximity switch by just 1 millimeter. These 90-degree blocks were also made in the last video. They're used to create 2 additional securing points of the base plate to the aluminum extrusion. They attach to the aluminum extrusion using a T-slot nut. On the perpendicular side is a threaded hole into which a screw is threaded that passes through the base plate. These may not actually be necessary, but they provide additional security to an overhead assembly. If making them again, I probably would change the design a little bit and make them 3 or 4 times longer. The small carriage of the miniature linear rail has a bit of play. The amount of play is fine for the prototype, but the next one will need to have either a longer carriage or 2 carriages on the linear rail. Now we need to create a clearance pocket for the motor. The boundary is marked with some tape, the motor is removed, and a Dremel is used to remove the material. The Dremel was woefully underpowered, but an air-powered rotary file made quick work of the pocket. The base plates are made on a large CNC router, and next time the pocket will be machined there. The motor slips right into the clearance pocket, and then we perform some final assembly. The dowel pin was a little too high, but is easily pressed lower. And finally, we can test fit the camera. To many, this is probably a pretty simple machine, but to me, not having made many machines, this is pretty exciting. While doing the voiceover, I see small things in the video that remind me of this. Like this, for example, after having assembled everything, just gently wiping the surfaces off. And finally, the camera is moving by computer control. Off to the side is a computer which is sending random absolute position commands between the two stops. The commands are text strings sent over Ethernet. Response codes and registers can be examined to determine the state of the motor. Small programs can be written to the motor to further abstract motion commands. For testing, a lab power supply provides 24 volts. Roughly 300 mA of current is necessary while the assembly is moving. When stationary, roughly 100 mA is necessary to power the driver and controller. The second output, supplying 7.2 volts, is for the camera. With flash enabled, roughly 2 amp of current is necessary for the camera. Removing the camera is easy, just remove the thumb screw, and then remove the battery adapter. Regarding motor current, with different run and hold current settings or different amounts of resistance to assembly motion, higher or lower amounts of current may be necessary. From overhead, we can see the action of the homing operation easier. The motor ramps up to and approaches the proximity switch at maximum velocity. After it senses the proximity switch has been tripped, it backs off of the proximity switch at a much lower speed. This works well except if the proximity switch is already tripped when the homing operation begins. In that case, it will proceed away from the proximity switch at the low speed. That may be okay unless there's a large distance for it to travel. In this design, since the proximity switch is forward of the absolute limit, the motor may need to initially move away from the proximity switch to home. If that occurs, homing takes a few minutes to complete, instead of a few seconds. These videos are mainly about the mechanical aspects of this machine. There's also a decent amount of software involved in coordinating motion and camera control. I wrote that software to run on Linux in Python. If you have an interest in the software, let me know and that can be a topic for a future video. This is the second video in a two-part series to build a linear stage for positioning. I was commissioned to build the linear camera stage, and that's really exciting, that there is a potential to earn a bit of a living from designing and building small machines using do-it-yourself CNC equipment. If you enjoyed this video, I hope you'll check out the others in this series. And until the next video, stay safe.